So, hello everyone. How are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are not gonna talk about any proof. We are not gonna talk about any constant. We are not gonna talk about actually mathematics, but we are gonna talk about Srinivasa Ramanujan. Okay, first of all, this is his work, like his life and his work. So basically, it's gonna be a long video, obviously, because we're gonna be taking a deep, you can say a deep travel of his life and his work of Ramanujan, actually, Srinivasa Ramanujan. And he was an Indian mathematician. He was an Indian genius, right? And we are gonna talk about him and his contribution in mathematics. And moreover, he was a genius. He was a literal genius. Okay, and before that, there's a disclaimer for you all, guys. Um, I have just passed my 12th this year, so please don't expect a lot of things from me. But still, I know a lot of things about Ramanujan, like his works. But still, there are a lot of things which I'm not sure about. Like you can say, there are a lot of things that Ramanujan did or invented that I'm not sure about yet. But yeah, I'll try to explain you all those things still, and but yeah, and I'm just a learner, right? I'm in the learning phase, and I don't know everything. I'm just learning, right? So I'm sorry, I'm accepting that maybe I would be defeated, actually, that I don't know, right? So please just bear with me about that. Okay, so let's just get back to this video. Okay, so basically it's a PPT made by Konkan University. It's a public university in um, Thailand, right? So I'm just gonna use the PPT of this PPT, actually, and and then we're just gonna talk about this crazy guy, actually, this crazy Indian genius. And I think this PDF or maybe this PPT is made by Michael Waldsmith. And I think, as far as I know, he is a professor, right? And I'm not quite sure about him a lot of things. So, okay, so yeah, let's just talk about this guy. And believe me, guys, this is gonna be a literal long video. Yeah. So please bear with me and just sit with me, listen to me carefully. That's all I want from you. So let's just begin. Srinivasa Ramanujan. Okay. So, in abstract, let's just read this out. This lecture includes a few biographical informations about Srinivasan Ramanujan, right? Among the topics which we discuss are Euler constant, nested roots, divergence series, Ramanujan natural equation, partitions, which Ramanujan was quite famous for. Ramanujan tau function, yeah, it's another thing for which Ramanujan is famous, actually. And Hardy Lidward, and there were a lot of things like the number pi. He was a player of pi, actually. So we're gonna talk about all those things. So let's just begin it. Okay, so Srinivasa Ramanujan, actually. He was born on 22nd of December 1887 in Erode. It's a small town in Tamil Nadu, right? It's like an Indian state in the southern part, actually. And yeah, so there he just took born, right? And he unfortunately died at a very young age, that is around 32 and 33 years of age. That's it. So that's a quite young age, right? So like yeah, so that's a quite young age to die. Obviously, it's very quite young age. And he just died in Chetput, Madras on 26th of April 1920. So he just born in 1887 and died unfortunately in 1920, right? So just take a look at this Indian genius. He was literal genius. Okay, let's just move on and let's just talk about the first biographer of Srinivasa Ramanujan, actually PKS, which is PK Srinivasan actually. So he was the biographer actually, right? Okay, so let's just talk about the biography of Srinivasa Ramanujan. So this is the lifespan of Ramanujan, right? Okay. So he in 1887 born in Erode near Tanjore. Yeah, I've never visited there, so I'm quite like uh, unstable there. Okay, okay. So he did schooling from 1894 to 1903 in Kumbakonam. Okay, it sounds like southern parts, right? And he did like in 1900s, right? In 1900, he began to work on his own mathematics, summing geometric and arithmetic series. So just take a look at this. So he just born in 1887 and he just began working on his own mathematics, that is around at the age of 13 years of age. So yeah, it was really young age to just at the age of 13 he was like learning geometric and arithmetic series, and even he was not learning, he was summing those things. Okay, so this is a temple, a holy temple in like Gopuram Sarangapani Kombakonam actually. And yeah, okay, okay, so this is the these are the house images, like images of his houses, I'm sorry, house. And yeah, just take a look at these things where this genius had spent his life. And here it is the statue, a small statue of Ramanujan in his own house. So yeah, it's very proud. And here is the hanged image of Ramanujan. Okay, so yeah, there are these are nostalgic things. Okay, so yeah, this was the school, town high school in Kumbakonam. So this was the school in which Ramanujan used to just attend his schooling, did his schooling actually. Okay, so in Town High School, Kumbakonam in 1903. So this was the final year of his schooling, actually, as much as I can say, right? Okay, wait a second, guys. Let me just fix this out. Okay, so G.S. Carr, actually, an author, a book named A Synopsis of Elementary Results, a book on pure mathematics in 1886, right? And it was like it was including 5,000 formulae, right? Okay, so this is a well-known, you can say, a well-known pair of equations, actually, pair of linear equations. I think it's not linear, but yeah, these are two equations which are quite difficult to solve actually. Even when I was in 10th standard, I used to just play around with these two equations, and believe me, nobody did solve this one. Even I didn't, right? But he just did solve these two equations, and he just found out that x was 9 and y was 4. Right, so yeah, I would request you to just solve these two equations by your own if you want to try this out. Okay, so biography continued. Okay, so in December 1903, exams at Madras University. Okay, so in January, right after this exams, he just got entry in Government Arts College, Kombakunam. Right. Okay, so he just got entered in Kombakunam Government. Oh, I'm sorry. Yeah, Government Arts College. Next, okay, and I think these are some prizes which Ramanujan did get actually, right? Okay, so by 1904, right, Ramanujan had begun to undertake deep research. He investigated this series actually. So let's look at this series, right? And this sounds like something sort of harmonic number, isn't it? So yeah, we'll just talk about these two things actually, these things later on. And he calculated Euler's constant to 15 decimal places. So it's another achievement, you can say. He began to study the Bernoulli's numbers. although this was his entirely own independent discovery. Yeah, obviously, because at that time it was quite rare that at this young age he used to just talk about these infinite sums, or you can say Bernoulli's number. So that's why he just did everything independently, right? Okay, and then here comes the harmonic number. Actually, it's the harmonic number, that is the sum as n goes from 1 to capital N, and it's 1 over n, right? So basically it's the sum of reciprocals of natural numbers, right? Okay, so I think this inequality had been discovered by Ramanujan itself, and by the help of that, Ramanujan, I think he just took care about this definition. Actually, this is the definition of the Euler's Mascheroni constant. So it's Euler's Mascheroni constant, right? So yeah, it sounds amazing that he just at the age of, I think I'm not wrong, but at the age, wait a second, 1904. So if we talk about 13, so at the age of 17 he was like just learning these things, right? So that was quite amazing. Okay, let's just talk about harmonic numbers actually. So we have harmonic numbers. We know that actually harmonic numbers is this one actually. Oh, wait a second. Capital N from small n to 1, from small n equals 1 to capital N of 1 over small n, which is 1 plus 1 over 2 plus 1 over 3 and plus dot 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 plus 1 over capital N. So this is the definition of the harmonic numbers. So your H1 is just 1, H2 is 1 plus 1 over 2, H3 is 1 plus 1 over 2 plus 1 over 3. So yeah. Okay, so yeah, this is the definition of the harmonic numbers as I just explained to you, right? Okay, so the sequence we can observe here that this is your H1, this is your H2, this is your H3, this is your H4. So that's gonna be like something sort of this 1, comma 3 over 2, comma 11 over 6, comma 25th over 12, comma 137 over 60. So that's something sort of that, okay? Okay, so if we observe the numerator, so that's gonna be 1, 3, actually the numerator of this sequence, right? So that's gonna be 1, 3, 11, 25, 137, and that's it keeps going up to something sort of these big values. And if we talk about the denominator, so that's gonna be 1, 2, 6, 12, 60, and something sort of this one. And it's just again just having some big values. Right. Okay, so if we talk about Euler in 1731, so the sequence, actually this one, right? Just take a look at this carefully. Has a limit, this Euler's Mascheroni constant, when n tends to infinity. So basically, if we talk about this, when n is tending to infinity of this argument, it's just Euler's Mascheroni constant, right? That's what this page is showing actually. And moreover, we have this amazing identity actually, and I would like to prove this down. Well, after this video, I'm just gonna check these things out, right? Okay, and here it comes the crazy, you can say the crazy invention of the Riemann zeta function, right? So Riemann zeta function. So Riemann zeta function equals this sum as n goes from 1 to infinity of 1 over n to the s, and that is equivalent to the product of primes of 1 over 1 minus p to the minus s. So that's crazy, right? That's crazy even. Okay, let's just talk about this. So yeah, we have talked about this thing, right? It's just this is just the harmonic number, and this is your minus natural logarithm of n. Now let's just talk about Bernoulli's numbers, right? So Bernoulli's numbers is B naught is 1. Okay, first of all, let me just say you a Bernoulli, like we have talked about the generating functions of Bernoulli's number. Wait a second, guys. Yeah, so we have talked about the generating function. So let me just write that down. So generating function of Bernoulli's number. Okay, so it was like x over e to the x minus 1 as the sum as n goes from 0 to infinity. I think it was um, bn and x to the n over n factorial. So this was the generating function that we have talked about in one of my earlier videos. So from here you can conclude that what is b naught and what is b1, and so basically here from here you can say b of 2k plus 1 when k is belonging to, you can say, the natural numbers, or you can say k minus 1 actually. So that's going to be 0. So the Bernoulli's number of odd arguments is 0 actually, right? Okay, let's just talk about this. So b naught times 2, oh, I'm sorry. Oh, I'm so sorry. I'm so sorry. I just did a mistake here. Actually, b of 2k actually is 0, right? Okay, and odds have values. I'm not, yeah, actually. I think I'm wrong now. I'm not quite sure about that actually. I think I have forgotten that. I must have forgotten that actually. Okay, so let's just talk about this. So from the generating function that I have written over here, so from this equation you can also derive b1, b2, and b3 actually, right? Oh, I think, yeah, okay. So your, let me just, yeah, now I can say that b of odd arguments, right? That is greater than 1 actually, greater than 1 is always 0. So basically your b3 equals b5 equals um, b7 is always 0, right? So yeah, this was the thing that I wanted to remember, but yeah, I'm done with this here. Okay, okay, so basically your b3 is 0 and your b4, when you just calculate either from here or from this generating function, you're gonna have minus 1 over 30. Okay, so let's just talk about the continued biography of the Ramanujan. So in 1905, fails final exam, and then in 1906 enters Panchayappa's College of Madras, right? So and then in 1907 December fails final exam again. So he was like, you know what? Why he just failed? Why he was like failing exams? Because he was scoring 100 out of 100 in mathematics only, but rest of the subjects he just used he used to get failed in rest of the subjects. So that's why obviously you need to get a minimum score in all subjects that you are studying, so in order to get passed. So that's why he used to get failed. Okay, so in 1908 he worked upon continued fractions, and this is one of his strongest, you can say, parts. Like literally I'm so amazed when I just look around his continued fractions. And then we have 1909 in April underwent an operation actually. I think he was suffering from something sort of disease, and on 14th of July 1909 he just got married with S Janki Amal. So yeah, that's quite a good news, isn't it? So yeah, she was the uh, like wife of Mr. Srinivasa Ramanujan. Okay, and then he just met Ramaswamy Iyer, and then first mathematical paper actually in 1911, and in club in 1912, Madras Port Trust. So get a scholarship for him from University of Madras starting. Okay, okay, so in 1912, questions in the Journal of the Indian Mathematical Society. So these were the infinitely nested integral, I'm sorry, infinitely nested, like you can say, infinitely nested square roots, of which values were asked, right? And the another one was this one. And guess what? This is this is another you can say foundation, or you can say another stuff that made Ramanujan so famous, because the way he just evaluated this sum was this you can say this infinitely nested square roots. It's crazy. So yeah, Ramanujan did evaluated it to 3, right? And for this one it was 4. So I think we'll talk about these two things later on. Actually, I'm just collecting things that I'm just going to discuss in future, right? Obviously. Okay, now let's talk about this one. So it's n times n plus 2. Okay. So n plus 2 whole squared can be written as 1 plus n plus 1 times n plus 3. So that's another great stuff you can say, because here you can say it's 1 plus n squared plus 3n plus n plus 3, right? So it's when you just add these things up, so that's going to be n squared plus 4n plus 4, and that is exactly the like when you just expand the n plus 2 whole squared, exactly stuff. Okay, and n times n plus 2 is another way of writing it is that is n times the square root of 1 plus n plus 1 times n plus 3. Actually, this is just n plus 2 whole squared, and the square root of it is just n plus 2. So basically, it's just written n times n plus 2. That's it. Okay, let's f of n equals n times n plus 2, and another f of n equals, okay, yeah, that sounds good, because let's just talk about this. So we have your f of n as n times n plus 2, right? So if we talk about here, so f of n equals n times, so when you just replace your n like n with n plus 1 here, so that's going to be giving us 1 plus n plus 1 times n plus 2, and that was exactly n times n plus 2. So these were the things actually Ramanujan did use to manipulate actually. So yeah, this is quite amazing, and this was actually right. Okay, and then let's just move forward from here. So we have f of n actually equals, okay, so he was trying to make some infinite, oh my goodness, just take a look at this. This f of n plus 1 can be written as n plus 1 times the square root. Oh wow, this is so amazing, guys. Just take a look at how beautifully he just expressed this. This is so amazing. I need to check this out once, but actually we are running out of time, so let's just move on. Okay, and here, oh, wait. Actually, he just generalized it when we just plug n equals 1, so it's 1 plus square root 1 plus 2 times square root 1 plus 3 times square root 1 plus 4, and dot dot dot, that just keeps going up to infinity, and which is 3. Wait a second. Oh my goodness, that's pretty amazing. Yeah, let's take a look at this. He just generalized that. Just take a look at the generalization that he did. Oh my goodness, that was amazing, literally. Okay, and another n times n plus 3. So I think it's for the second one actually. So it can also be written as n plus 5 plus n plus 1 times n plus 4. And again, just assuming it g of n. So yeah, and again he just did that. He just generalized it as well. So when you replace n with I think 2, I'm not sure, yeah, okay, 1. So when you replace 1 actually, so that's going to be giving us the same one that was the second question asked in the general of Indian Maths Society, I'm not sure, yeah. So this was Ramanujan actually. He just didn't solve that thing but generalized a whole formula. So that's, you can say, the real mathematics, guys. Okay, so here comes actually letter of Srinivasa Ramanujan to M.J.M. Hill in 1912. Okay, this is another crazy invention, or you can say crazy discovery of Ramanujan. Okay, I know a couple of ways by which we can just prove this down. The first one, I have proven this one. I have taken a dedicated video to prove this down using Grande series actually. So if you want, please consider watching that video actually. Yeah. And the second one is we have a well-known formula for the Riemann zeta of negative n as uh, minus of b of, I think it's n plus 1 over n plus 1. So if we replace n with 1 here, so basically it's Riemann zeta of minus 1. It's the sum as n goes from 1 to infinity of n, right? And that's the actually this was the Ramanujan's paradox, right? So it's coming out to be minus of b2 over 2, and b2 is your 1 over 6 actually. So b2 is 1 over 6. So basically it's minus 1 over 6 times 2, which is minus 1 over 12. So another proof, actually, we just did it right over here using this very well-known formula. Although I just used this, but I have never proved that down. But still, I will be just proving that down soon. Don't worry about that. Okay, and here comes this one. Again, why? Because using the same one actually that just we just used on the previous page. So if we plug n as even, right? And obviously greater than 1, right? Obviously. So it's gonna be Riemann zeta of negative e1, right? And it's gonna be minus of b odd, and this odd is greater than 1. So for that case, odd as well. So for that case, it's always 0, right? So basically, Riemann zeta of minus 2 equals Riemann zeta of minus 4 equals Riemann zeta of minus 6, and dot 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 all the way up to infinity is always 0. So yeah, it's just the you can say the magic of Bernoulli's number. And for the odd, like I'm sorry, the cubed of the natural numbers, the sum of cubes of natural numbers is 1 over 20. Again, using the same stuff, using the Bernoulli's number. Actually, B4 was 1 over 120, I think. I'm not sure about that, but when you use that, you gonna see that it's gonna work out. Okay, so these things are like well-known things actually, and we just got to learn these things. Although I haven't proved this yet, but it's not that difficult to prove this down. And again, I'm not gonna just prove this in this video actually, because that's gonna be quite delay, right? Okay, so a need renormalization of divergence series, Leonard Euler. Okay, let's talk about this. Okay, so here it comes, guys. Just take a look at this. So for n, oh wait a second, actually it should have k here. So for k greater than or equal to 1, this condition or this formula satisfies actually. And yeah, with the help of that, it's an amazing stuff, right? It looks amazing. Okay, so yeah, actually when n is greater than 1 or equal to 1 actually, obviously. So Riemann zeta of minus 2n is going to be 1 to the 2n plus 2 to the 2n. So that's always going to be 0, because we would be having b of odd, and that 2 greater than 1. So for that case, it must be 0. So that's why we would be having zeros only. And yeah, it's these two things are quite easy to just evaluate actually. Okay, and another Riemann zeta of minus 5 using the Bernoulli's number. You can just find that as well. Okay, G.H. Hardy, Divergence Series, 1949. So Niels Henrik Abel, a mathematician, yeah. Divergence series are invention of the devil. Wait a second, and it is same for So based on them demonstration whatsoever. Oh, I need to go in mathematics. Letter of Ramanujan to Hardy, January 16th of 1913. So I have had no university education, but I have undergone the ordinary school course. After leaving school, I have been employing the spare time at my disposal to work at mathematics. Okay, I have not trodden through the conventional regular course which is followed in a university course, but I am striking out a new path for myself. I have made a spatial investigation of divergence series in general and results I get are termed by the local mathematicians as starling. Okay, so this was the letter actually. And you know what, at first just take a look at this. You would say, whoa, what are you talking about actually? You haven't taken any like university education, you haven't enrolled yourself in mathematics degree, and you are doing something great. So at first everyone would say, oh, you were just talking unnecessary stuff. But actually he was this thing, he was Ramanujan. So here, okay, so he was the here it is, the Godfrey Harold Hardy, or you can say G.H. Hardy. I think he was an English mathematician, right? Okay, and I think another mathematician, I'm not sure, but he was with the G.H. Hardy actually, John Edensor Littlewood, Hardy and Littlewood actually. So, okay, okay, letter from Ramanujan to Hardy. So actually, in the letter, Ramanujan did solve this infinite sum. That is the sum. You can say, well, if I'm just gonna write this in terms of this thing. So this sum this sum actually. So it's uh, you can say -1 to the n plus 1, right? And it's n, right? When you just plug n equals 1. No, actually it's -1 to the n. No, actually, yeah. Okay. So basically here we are having a negative in front of the even terms actually. So for that case, if you plug n equals 1, so plus 1, actually it's 1, and -2 plus 3 minus 4. So that's going to be evaluated to 1 over 4. And this is another groundbreaking, you can say. This is, I have never seen these things. And this is 1 minus 1 factorial plus 2 factorial minus 3 factorial plus, you can say, 4 factorial, and yeah, 4 factorial minus 5 factorial. So it's a 0.596 or something sort of that. So yeah, it's quite impressive. So answer from Hardy, 8th of February 1913. So he just wrote that I was exceedingly interested by your letter and by the theorems which you state. You will, however, understand that before I can judge properly of the value of what you have done, it is essential that I should see proofs of some of your assertions. Your results seem to be fall into roughly three classes. The first one, there are number of results that are already known, okay, or easily deducible from known theorems. Okay, so basically, G.H. Hardy said there were a lot of theorems which were already known, but maybe due to some lack of resources to Ramanujan, that's why he couldn't found. But again, he just anyhow discovered those theorems which were already discovered. So, yeah, the first one. And the second one is there are results which, so far as I know, are new and interesting, but interesting rather from their curiosity and apparent difficult than their importance. So again, the difficult words from Hardy actually. And the third one, that is there are results which appear to be new and important. Obviously, he was Ramanujan, so he did a lot of things. So in 1913, on 27th of Feb, New letter from Ramanujan to Hardy. So a new letter from Ramanujan to Hardy. Okay. And visit of Neville to India. Not, whoa, what's that? And in 1914, 17th of March to 14th of 11, traveled to Cambridge. Actually, he took almost a month to travel from India to Cambridge. At Cambridge, actually, right? And yeah. So in May of 1918, fellow of the Royal Society, fellow of the Trinity College, actually, Ramanujan did got this position actually, right? And due to some sickness, you can say Ramanujan traveled back to India in 1919 on 27th of Feb, and he just reached here in India on 13th of March. Okay, Ramanujan, taxi cab number 1729. This number is itself very crazy. It's itself a mystery, you can say. Hardy's obituary of Ramanujan. I had ridden in taxi cab number 1729 and remarked that the number 7.3 13.19 seemed to be rather dull one. Wait a second. So let's just take a look at the beauty of this number actually. This is 1 cubed plus 12 cubed, and that too equals to 10 cubed plus 9 cubed, right? Just take a look at this. And just imagine these coincidences that were happening with Ramanujan, right? Okay, okay, let's just move on. And another, you can say 50. So 50 is another number which can be expressed into two different, you can say, sum of squares. That is 7 squared plus 1 squared and 5 squared plus 5 squared. And there were a lot, like Ramanujan found it, 4104. It's 2 cubed plus 16 cubed, and that equals to 9 cubed plus 15 cubed. 13832, 2 cubed plus 24 cubed, and 18 cubed plus 20 cubed, and that just keeps going up to infinity. So that was actually Ramanujan. Leonard Euler. So Euler did find this actually. He was like, obviously, uh, we cannot compare mathematicians, but you can say if Ramanujan would have lived more than 33 years only, so he would have reached up to the level, or maybe he would have crossed the level of Euler or Gauss, right? So these two, you can say, but unfortunately, I don't know what just happened, and he just passed away at a very young age. Diophantine equations actually. So x cubed plus y cubed plus z cubed equals w cubed, right? Okay, and uh, these are the values which is gonna satisfy this equation. So these things were literally amazing, you can say, because these things require a lot of time, a lot of brain, a lot of, you can say, thinking power. That yeah, you can think about those at that level, so that you can find these things. So yeah, it's just take a look at this. When you plug x equals 3 and y equals 4 and z equals 5, so it's 3 4 5, and the sum of the cubes of these three numbers is gonna be 6 cubed. Oh my goodness, just take a look at the beauty of these things actually, guys. Wow. Nagel equation. So let's just take a look at this thing actually. Wait a second. I need to just fix this out. Yeah, okay. Wait a second, guys, actually. I hope you guys are having fun. And okay, so it's x squared plus 7 equals 2 to the n, right? Okay, so okay, let's just take a look at the beauty of this. When x is 1, your n is 3 actually, right? and when x is 3, oh, so yeah, so it's 2 to the fourth. When x is 5, so it's 2 to the fifth. X is 11, 2 to the seventh. X is 181, 2 to the 15th. Oh my goodness, like how can someone do all these things in a very short period of time? Like literally, dude, I'm blown. I have my mind is blown right over here. Not still, because we have to see a lot of things yet. We have not seen everything actually. Okay, so let's just move on. At most one solution. Okay, so now let's talk about partitions. And Ramanujan was like famous for this partitions actually. And actually, you know what partitions is? It's the number of ways by which you can write a number into, you can say, sums of natural numbers. Like, let's just take this one. So one can only be written in terms of 1 plus a 0, although we won't consider 0 actually. 2 can be written as 1 plus 1 only, right? Sum of natural numbers. 3 can be written as 1 plus 1 plus 1, 2 plus 1, right? So let's just take a look at this. 3 is 2 plus 1 equals 1 plus 1 plus 1. So the number of partitions of 3 is 3. The number of partitions of 2 is 2, right? So basically, why it's 2 is because 2 plus 0 is also included, right? So okay, now let's talk about a number of partitions of 4. So 4 can be written as 1 plus 1 plus 1 plus 1, or you can say 2 plus 2, or 1 plus 1, wait a second, 1 plus 1 plus 1 plus 3, or you can say 2 plus 1 plus 1, right? So it's already 1, 2, 3, and 4, right? And we are left with uh, 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 another one, that is 4 plus 0. And yeah, so it's done, right? It's perfectly done now. So yeah, partitions actually. And consider this: the number of partitions of 5 is 7, the number of partitions of 6 is 11, the number of partitions of 7 is 15, and that just keeps going up to, that just keeps going. Okay, is a multiple of 5. Okay, just take another look here. So the number of partitions of this type of number, that is 5n plus 4. So like this is including, you can say, when you plug n is 0, it's 4, 9, or your when you plug this, so it's 14 or it's 19. So these type of numbers would be having the number of partitions of multiple of 5, right? Basically it's 5. The number of partitions of 4 is 5, right? And maybe it would have 10, right? Obviously, because it's the much multiple of 5, right? So the number of partitions of 9 is 10, and the number of partitions of 14 is 15. The number of partitions of 19 is 20. So yeah, this is how you can understand. And these type of numbers would have 7, 11. Just take a look at this actually. This is 5, so it's quite like being connected to that one. The coefficient of n is also related to the number of the multiple of number of the actually the multiple of number of partitions actually. I hope you all are getting that. So you can consider these things right now. Let's just move on. Partitions actually. Kane Ono. Manjul Bhargava, right? So it's Manjul Bhargava, and he is the Manjul Bhargava, and he's an Indo American mathematician, Indian American mathematician, you can say, and he might be like Ken Ono, right? And and Kane Ono in front of Ramanujan's house. So let's just talk about this. Okay, so here comes another crazy, you can say, um, Leonard Euler's identity, right? for partitions, number of partitions actually. So let's talk about this. So 1 plus p of 1 times x plus p of 2 times x squared plus dot 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 all the way up to p of n times x to the n, and that's keeps going up to infinity, equals 1 over the infinite product, that is 1 minus x times 1 minus x squared times 1 minus x cubed dot 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 all the way up to 1 minus x to the n, and that just keeps going up to infinity. And guys, you know what, I would be grateful to just take a look at the proof of this identity. And yeah, at the end of this video, I'm just gonna take a look at the proof of this one at the very beginning, actually, at the very first, because this looks amazing. You are saying that 1 plus the sum as n goes from 1 to infinity of p of n times x to the n equals the product as n goes from 1 to infinity of 1 minus x to the n whole to the negative 1. So that's pretty amazing, and these things were like great mathematicians can all could only do that, right? Okay, let's talk about Eulerian products. Oh yeah, Riemann zeta function for s greater than 1 actually. And this is another great discovery of Leonhard Euler again. So basically it's Riemann zeta of s, and it's the sum as n goes from 1 to infinity of 1 over n to the s equals the product as p goes, actually the product of primes actually, prime numbers of 1 minus p whole to the negative s, and that whole to the negative 1, right? This is the Riemann zeta function was given by this guy, that is George Frederick Bernhard Riemann. And I think as far as I know, he was a German mathematician, right? Yeah. Okay. Okay, and now let's talk about Ramanujan tau function. Oh, guys. So basically, these are the things that I can openly say that I'm not sure about these things a lot. Right. So basically, we have this identity that is x times a 1 minus x whole to the negative 1 equals the sum as n goes from 1 to infinity of x to the n. Let's just talk about this. Well, we know that 1 over 1 minus x equals the sum as n goes from 0 to infinity of x to the n. So basically multiplying both sides with x, that's going to be giving us x over 1 minus x equals the sum as n goes from 0 to infinity of x to the n plus 1, right? So basically when you replace n plus 1 with k, so when k is when k is 0, n is k, when n is 0, k is 1. So from here you can say x times 1 minus x to the negative 1 equals the sum as k goes from 1 to infinity of x to the k, or you can use n rather than k. It's just the index variable, right? So yeah, it was the same stuff that you just need to multiply this equation with actually. Okay, and next we are done with that, and now we have the tau function. I think this is the generating function of tau, and x times the product as n goes from 1 to infinity of 1 minus x to the n whole to the 24 equals the sum as n goes from 1 to infinity of tau of n times x to the n, right? So I think it's the generating function of Ramanujan's tau function. Okay, next we have another equation for Ramanujan's tau function that is being related to the product of prime numbers, that is the sum as n goes from 1 to infinity of tau of n over n to the s, right? And that is being equals to the product of prime numbers of, wait a second guys, oh uh, okay, the product of prime numbers of yeah, 1 minus tau of p times p to the minus s plus p to the 11 minus 2s and whole to the negative 1, right? So actually, you know what, I need to check these things out firstly by my end, and when I'll be done once, then I'll surely share all the things with you all. Okay, Ramanujan's congruences. So tau of p times n is divisible by p for p equals 2, 3, 5, 7, 23. So yeah, I'm not sure about these things, so I just need to check those things out once. So Pierre Deligne actually, Ramanujan's conjecture. Okay, so I think this is the Ramanujan's conjecture, which was solved by Pierre Deligne, this guy, in 1974. Right. Okay, that sounds good. Okay, and let's just get back to Hardy Ramanujan. So for almost all integers n, the number of prime factors of n is log times log, log of n. Oh my goodness, that sounds crazy, isn't that, guys? And again, guys, you know what? I'm not quite sure about these things, so I just need to check these things out once, and then I'll certainly share all these things to you guys. And you know what? Like, if you're a daily viewer of my channel, so you must have recognized that it's not, these things are not like, I don't study these things actually, but yeah, I need to, because it's the Ramanujan stuff, and yeah, but yeah, surely I will study all these things once I'll just once I'll just get finished with the things that I love to do from this PPT, and then I'll surely move to the one which I need to do actually. Okay, here comes the approximation for pi due to Ramanujan. Oh, wait a second. 63 over 25 times 17 plus 15 times square root of 5 over 7 times 15 times 7 plus 15 times square root of 5. Guess what? If you solve this, so you're going to have 3.141592653. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 9 decimal places, the value is same that this was by Ramanujan. Oh my goodness, can you believe that this guy was this guy was literally crazy? Not in that manner actually. And if you talk about the error, so it's around 0.00000000022, and that's, yeah. So it's extremely low. So that was actually Ramanujan. And here comes the beastie formula for Ramanujan's, like pi from Ramanujan. Pi equals 9801 over square root of it. Actually, can you imagine that Ramanujan did something that he just showed pi as an infinite sum, and that too is these kind of like arguments. So can you imagine, like literally 9801 over square root of 8 times this sum as n goes from 0 to infinity of 4n factorial times 1103 plus 26390n over n factorial to the fourth, and times 396 whole to the 4n, and that too whole to the negative 1. Oh my goodness. So when you plug n equals 0, right? So when you just plug n equals 0 and find the first term of this infinite sum, and when you just solve those things, so that's going to be giving us 6 exact digits for pi. That is, you're going to have this result, and this is the 6 exact digits that is going to match with pi. And look at this, Ramanujan's formula for 1 over pi. So 1 over pi equals the sum as m goes from 0 to infinity of 2m choose m times 42m plus 5. Oh my goodness. Over 2 to the 12m plus 4. Okay, decimals of pi. Ramanujan's formulae were used in 1985, and 1.7 times 10 to the 7 digits for pi actually. So it's 1.7 crores. So you imagine that from the formulas of Ramanujan for pi, the digits that are being like same, or you can say similar, is almost 17 million digits. Oh my goodness, that's itself so crazy. So you can read this out if you want. In 1999, we were having 2,000 crores. So yeah, okay. Let's just move on. Okay, last work of Ramanujan, right? So mock theta functions. Okay, so we will be just looking at the mock theta function actually. But before that, let's just take a look at this Sastra Ramanujan Prize, right? So Sastra Ramanujan Prize, I think it's Catherine Brinjman International Conference in number theory and mock theta functions, Srinivasa Ramanujan Censor Konam actually, okay. And yeah, here it is the Manjul Bhargava who also got the Sastra Ramanujan Prize. And this guy is the greatest mathematician alive. So he's Terence Tao, and he's a professor in University of California, Los Angeles. And if we talk about wait a second, yeah, if we talk about Manjul Bhargava, so he is a professor at Princeton University, and both guys are field medals winners as well, fields medal actually. Okay, and now let's just move on. Okay, so Ramanujan according to Wikipedia. So we are just gonna talk about Ramanujan according to Wikipedia as well. So we are just gonna look at these things actually. Landau, Ramanujan constant, Ramanujan prime, mock theta functions actually, and Ramanujan Soldner constant, Ramanujan theta functions, Ramanujan's sum, Rogers Ramanujan identities. Okay, guys, let's just talk about this. It's interesting. Landau Ramanujan constant. I think I'm pronouncing it wrong. I'm not sure. Okay, let's just understand this. So basically, it's a constant occurs in number theory, result in starting with the number of positive integers less than x, which are the sum of two squares for large x. Okay, so basically, what does that means is when you plug x equals 5, so your capital N of 5 is just 1 because the sum of the squares of two positive numbers should be less than the x actually. So this is the only possible way by which you can say that yeah, the sum of two squares is less than x, which is 5. So 1 squared plus 1 squared is 2 actually. But if you talk about 1 squared plus 2 squared, so it's 5, which is not less than 5, right? So and if we talk about n of 20, right? So it is 1 squared plus 1 squared less than 20, which is just 2, right? Let me just write this down. Let me just use color, right. So this is your 2, this is your 5, this is your 10, this is your 17, this is your 8, this is your 13, and this is your 18. So basically all these things are less than 20 actually: 2, 5, 10, 17, 18, 13, and 18. And that is why there are 1, 2, 3, 4, 5, 6, 7. So n of 20 is 7, right? And n of 5 is 1. Right. So yeah, basically this is the Landau Ramanujan constant, and actually, it's not talking about small quantities, that is 5 or 20. It's talking about when x is tending to infinity. So when x is tending to infinity, so n of x times square root of natural logarithm of x over x is equivalent to 0.764223, and yeah, that's a constant actually. So that's pretty amazing. Yeah. Okay. And I'm not sure about this thing, guys. Actually, Ramanujan primes, and if you when you doubt, I'm sorry, if you guys are familiar with this, please tell me in the comment section. I'd be grateful to know about this thing. Okay, let's just move on, and we have the Ramanujan-Soldner constant. In mathematics, the Ramanujan-Soldner constant is a mathematical constant defined as the unique positive zero of the logarithmic integral function. It is named after Srinivasa Ramanujan and Johann George von Soldner. So basically, this is the Ramanujan-Soldner constant, and this is Ramanujan's sum, right? So in number theory, a branch of mathematics, Ramanujan's sum, usually denoted with C sub q of n, is a function of two positive integers variable, that is q and n, defined by the formula c sub q of n is defined by the sum as q is greater than a and a is greater than 1. Q is greater than equal to a and a is greater than equal to 1 actually, and the Pochamer symbol of a sub a of a and q is 1, should be 1 actually, of e to the 2 pi I a over q times n. So basically Ramanujan's sum are used in the proof of Vinogradov's theorem that every sufficiently large odd number is the sum of three primes. Okay, here comes the Ramanujan's theta function, right? Okay, so basically it is defined by f of a b equals the sum as n goes from negative infinity to infinity of a to the n times n plus 1 over 2 times b to the n times n minus 1 over 2. Okay, you know what, guys? We are having a Jacobi theta function as well, and I have talked about this one. I have used this one to prove the functional equation of the Riemann zeta function, right? So basically, it's theta of t equals the sum as n goes from negative infinity to infinity of e to the minus pi n squared t. And a well-known property, that is theta of 1 over t was equals square root of t times theta of t. So yeah, these things were, I just used these things to prove to prove the functional equation of the Riemann zeta function. And if you're a daily viewer of my channel, so you must have remembered that. And we have Rogers Ramanujan's identity. Although we're not gonna talk about these things, but I think I'm gonna take another dedicated video to talk about the Rogers Ramanujan identity. That they are great actually. Okay, so this is another the basic you can say the geometric series, actually infinite geometric sum. So when you replace z with negative 1 as Euler does, so that's going to be giving us 1 minus 1 plus 1 minus 1, and that's just keeps going up to infinity, and the result is 1 over 2, surprisingly. Right, and this is, guys, believe me, this is known as the Grande series, which we of what we have talked about in this video. And using the Grande series, I have just proved the Ramanujan's paradox, that was the sum of all natural numbers. That is 1 plus 2 plus 3 plus 4, and that's just keeps going up to infinity, was equals minus 1 over 12. So using the Grande series, I have just proved that. Please watch that video. And here we have 1 over 1 minus z squared. Actually, if you take the derivative of this function, so that's going to be giving us this one. So yeah, similarly from the derivative of the previous series, so taking the derivative of this equation with respect to z, so that's going to be giving us 1 over 1 minus z whole squared equals 1 plus 2z plus 3z squared plus 4z cubed, and that just keeps going up to infinity. And if we plug z equals minus 1, actually z equals minus 1, so that's going to be giving us 1 minus 2 plus 3 minus 4 equals 1 over 4, of which we have talked about in the middle, I think in the middle of this video, right? Do you remember? Okay, and then he just played around with these sums actually. I think he just yeah. Okay. Okay, next let's just move on. And convergence, actually I'm just working on convergence and divergence, so I think I won't be able to just tell you about these things. So I'm so sorry, guys. Actually, I just need to get passed through these things actually. Okay, yeah, do you remember that we have talked about this one, why this is zero actually? Because of the Bernoulli's number, right? And yeah, again, here it is. And we have some examples of the divergent series. 1 plus 1 plus 1 up to infinity is 0. Surprisingly, again, it should be divergent, but it's surprisingly 0. So it was Ramanujan. He was a player of series, actually divergent series. So 1 plus 2 plus 4 plus 8, and that's just going up to infinity, is minus 1. Right. Okay. And we have Euler. Wow. 1 minus 1 factorial plus 2 factorial minus 3 factorial plus 4 factorial, and that's just going up to infinity. It is unbelievably evaluates to minus e times Euler mascaroni minus 1 plus 1 over 2 times 2 factorial minus 1 over 3 times 3 factorial. That's just keeps going up to infinity, and this gives the value of also found by Ramanujan. So these things were those things which were discovered by Ramanujan, right? Maybe because of lack of resources that he would have find that, yeah, it is discovered by Euler already. Yeah. Okay, and we are here with our final page actually, and this is a well-known infinite sum. Actually, this is quite easy to evaluate, but the thing is that right now I'm just forgetting the thing that we need to just talk about this, but it's all right, it's easy. I'm sure I have seen this song. Okay. Oh, guys. So successfully we are at the end of this whole PPT, which was about the Indian genius Srinivasa Ramanujan. He was really he was a really great mathematician. But the thing is that he just passed away at a very young age. That was just 33 years of age. But if he would have lived longer, I can surely say that he would have done a lot of things like Euler and Alfred Gauss had done actually. But it's all right. Um, let's say rest in peace, Mr. Srinivasa Ramanujan, and we love you. You did a lot of things for us, and yeah, thank you for being a part of this world. And I'm gonna thank I want to thank to the Khan University to provide me this PDF actually, not directly, but I just got this PDF on web actually, right? So yeah, with that said, goodbye guys, take care, love you. And again guys, if you got to learn something out of it, actually not my video, it's Srinivasa Ramanujan. So if you got to learn something out of Srinivasa Ramanujan's life and his work, please make sure to like, subscribe and share. And if you have any kind of doubts so far, you are free to ask me in the comment section. If I would be able to reply over your questions, I'll surely reply over questions. And please share where I just got struck in this video. Like, you just have to explain me, right? That yeah, this thing is something sort of this you don't know about. Yeah. So, yeah, goodbye, guys. Take care. Love you, and just love mathematics. Learn mathematics, and love these mathematicians because they have done a lot of things. Don't hate them actually because they did a lot of things, but love them because they had made our life easier, right? So, yeah, I think it's fine, and let's just meet up in the next video. And goodbye, guys. Yeah, very goodbye. Love you.